Hello, everyone. We've been talking about differential equations for the past few lectures. And what I want to focus on today is a particular type of first-order differential equation called linear equations. And what we're going to see in this lecture is that we can solve these explicitly. I can tell you exactly what y is equal to as a function of x. Now, let me show you the types of equations that I'm going to talk about. You can write these equations in this form. I'm going to use y prime to denote dy by dx, just because it's slightly more convenient to write the prime throughout the lecture today. And we are going to look at differential equations that look like this. Okay, so what this is called is standard form. And standard form of what, you ask? Well, this is the standard form of a first order linear differential equation. So first order. Why is it first order? Well, we talked about this in the previous few lectures because it only contains one derivative in y. So the order is the number of derivatives. First order, first derivative. Linear, why is it linear? Well, the only power on y that you're seeing is 1, right? So that's this term right here. That term is linear in y because the power on the y is 1. So if that was a y squared there instead, it would no longer be a linear equation. And then differential equation. Why is it a differential equation? Well, it's an equation that involves the derivative, the differential part of an unknown function y. And so, of course, the goal with this all the time is to figure out what y is. In the previous video, we saw we can estimate or approximate what that function is using Euler's method. But one of the things, if you remember from the code that I showed you, is I had the exact answer. So the question is, how did I get it? Well, the equation that we used was a first order linear differential equation. And so by the end of this lecture, you'll be able to solve that yourself. You'll be able to figure out what exactly that exact solution is. Now, we have actually already seen first order linear differential equations before. Our exponential growth and decay model is in fact a first order linear equation. So decay model. This was, if you remember, given by y prime is equal to k times y. Now, we want to write everything today in terms of the standard form. So you can see that all of the y's and the y primes are on the left-hand side of this equation. Everything that just has an x is on the right-hand side. So the standard form here, well, the standard form is given by just pulling that ky onto the left-hand side. So in this case, p of x is equal to minus k, and q of x is equal to 0 when you write this thing in standard form. Okay, so we have seen these before. This is, we called these things separable equations because you could separate out the x's and y's. In the case of these first order linear differential equations, they're not necessarily separable. They're only going to be separable if q is equal to 0. So we have a much larger class of equations that we're going to work with today. Let me give you another example, just so that we can really see what standard form is supposed to look like. So let's ask ourselves to put the following equation in standard form. Okay, so we have x, y prime is equal to x squared plus 3y. Well, again, we want all the y's and the y primes on the left-hand side. So let's start with that. X, y prime minus 3y is equal to x squared. Now, at this point, you might be tempted to say that maybe p of x is equal to minus 3 and q of x is equal to x squared, but that would not be correct. look at my standard form at the top here. There is no function in front of the y prime. So the only way this is going to work is if we divide off the x. So if we divide off the x term, I get y prime. That's correct in terms of the standard form. Minus 3 over x, y, that's okay in terms of the standard form. Everything in terms of y is on the left is equal to x. And this is assuming, of course, x is not equal to 0. But what this tells me now is that p of x is equal to minus 3 over x, and q of x is equal to x. So we have to be careful, right? It's very, very specific how these things look. And the reason that we have this standard form is because we use the standard form to come up with a solution. So if you are going to solve these things, you need to have them in standard form if you want to follow the techniques that I'm about to lay out. So solving linear equations. So what are we going to do? Well, basically the goal is to multiply this by some function v so that we can get rid of the derivatives on the left-hand side. Okay, so again, we know that getting rid of derivatives essentially comes down to doing an integration. So somehow we need to do some integration in here. And let me show you how we're going to do this. Okay, we've got y prime plus p of x y is equal to q of x. I'm going to multiply everything by v of x. Okay, so I want to emphasize that v is just a function of x. So I get v of x y prime plus, I'm going to write p of x first, then v of x. So I'm just going to write it alphabetically. And then, well, in this case, it's not going to be alphabetically. It'll just be v of x, q of x. I know that it's slightly confusing, but there's a method to my madness if you bear with me. Here's what we want, okay? And we'll come back to what this means or how we can actually get this, but I want to be able to write the whole left-hand side as the derivative with respect to x of v times y. Okay, we will come back to this in a moment, but bear with me. That's what I want to be able to do. And this will be equal to v of x, q of x. But now we can see that on the left-hand side, we just have a derivative. So we can undo that thing with an integral. So I get v of x, y. This is equal to the indefinite integral, so the antiderivative of v of x, q of x, dx. And this tells me that y is equal to 1 over v of x, the integral of v of x, q of x, dx. Okay, so you can see that there's some pieces that are sort of built in here. First of all, v has to be non-zero, right? That's the only way this is going to work, is if v is non-zero. Second of all, I did not overcome this jump here. I said that that's what I wanted to be able to do, but I haven't figured out what v actually should be to be able to do this. So let's ask ourselves, what is v? Well, what we wanted to satisfy is we wanted to say the derivative of v times y is equal to v times y prime plus p v y. So I suppressed all the dependence on x. And if you're wondering where that equation came from, it's exactly what I wanted to achieve. So I have, maybe if I use some colors to highlight this, this was the right side of my equation. This was the left side of my equation. And I want those two things to be equal to each other. So I set them equal to each other, and I ask myself, what does it take to make these two things equal to each other? Well, on the left-hand side, this is a product. I can use the product rule. So this is vy prime plus v prime y and this is equal to Vy prime plus P Vy. And now you can see that the Vy primes are going to cancel on both sides. And this is going to give me, pardon me, this is going to give me V prime y is equal to P Vy. And now I can cancel out the y's as well here. And I get a differential equation in terms of V. So I get V prime is equal to P times V. And this thing right here, this is a separable equation. And if you go all the way back through, 3-4 weeks ago worth of lectures, you're going to find that we can solve separable differential equations, right? You've actually already done it. You might have forgotten, but we did do this. And so this is going to give me, if I write V prime as dv dx, so let me just write that step. Nothing changed yet. We just know that we use this notation for separable differential equations. I get dv over v is equal to p of x dx. And I wrote p of x because I want to emphasize that this is a function of x now. Now I hit both sides with an integral. And I get this. Without knowing what p is, I can't do anything on the right. But on the left, I get the logarithm of v. And we're hoping that this thing is going to be positive, so I didn't put any absolute values around it. Again, that positivity, that's coming from the fact that we divided by v earlier. And here I get the antiderivative of p of x dx. And solving for v gives me v is equal to, so raise both sides to the power of e, the integral, the antiderivative of p of x, raise that thing to the power of e, and now you've got your, what we call our integrating factor. So let's call this thing v equals our integrating factor that will help us to solve the differential equation, right? So don't lose sight of what we did here. We said that if we find this v, then the solution to the differential equation is 1 over v times the antiderivative of v times q. Okay, so that's a lot to digest, right? It feels like a lot, but I will, maybe I will make you happy by saying most of the difficulty here is in what we just did. Putting it into practice is actually a much easier thing. So let me illustrate by example. So let's do an example here. Let's say solve the equation. So solve the equation, that one that we started with, x y prime is equal to x squared plus 3y. Okay. So what we already did is we put this thing in standard form. That's going to tell us what p and q are. So in standard form, we got y prime, minus 3 over x, y is equal to x. And we know that p of x is equal to minus 3 over x. Q of x is equal to x. Okay, now that we've identified p and q, we can get the integrating factor. So integrating factor, that's v of x. So v of x is equal to e to the antiderivative of p of x, which is equal to e to the antiderivative of minus 3 over x dx, which in our case is equal to e to the minus 3 natural logarithm of absolute value of x. In this case, we don't have to worry about the plus c yet, because we got to pick the function v of x. Okay, so we don't need it yet. You'll see that the integrating factor will eventually come through. Now, what we have here is E. We can use our properties of ln, and we can say ln of x to the minus 1/3. And in our case, I'm going to put a little note. We're going to restrict to x positive so that I can get rid of that absolute value there. So a lot of the time when you are given these differential equations, you're given a domain for x as well. So in our case, we're going to assume that x is positive. And so now we have e to a ln. Well, those things cancel each other out, and I get an integrating factor of x to the 1/3, which is, or sorry, x to the minus 3, which is the same as 1 over x cubed. Okay, that's the first piece of this. Now that we know v of x, we can multiply it into the differential equation. So follow me. What happens? So let's multiply by v of x. Well, then this is going to give me 1 over x cubed, that's v of x, times y prime minus 3 over x y is equal to 1 over x cubed, that's v of x, times x, which is q. Okay, so I get 1 over x cubed, y prime, minus 3 over x to the 4, y, and this is equal to 1 over x squared. And now with an explicit v in there, you can see the product rule in action. It's kind of weird to go backwards, but you can see that this is actually the product of 1 over x cubed times y, and then you take the whole derivative of that. So if it makes it easier for you, try and go this way and see how the product rule is coming into play here. And then on the left-hand side, I just get 1 over x squared. I can integrate both sides, and this gives me 1 over x cubed y is equal to the antiderivative of 1 over x squared. And so now I get 1 over x cubed y is equal to, in this case, you get minus, pardon me, it's very sensitive today, sorry, minus 1 over x plus c. And so you can see that the integrating constant came through, the plus c, and you can isolate for y, and this will give you, multiplying through by x cubed, you get x cubed minus 1 over x plus c, which finally gives you the final solution here, minus x squared plus c x cubed. And we've seen this is for x greater than 0. We've seen this before, that plus c in there, that constant c is going to be determined by a particular solution. So for example, with the Euler method, we saw these initial value problems, and they pin down a particular solution. In the same way, this gives us a family of solutions that satisfy the differential equation, and we can pin down a particular one by being given a point on the curve. Okay, let me give you an example of that, of exactly what I'm talking about here. So let's just work through another example. In this case, we're going to be given an initial value problem. So let's imagine we have the following example. Find the particular solution So particular solution, that's unique. In the previous case, the C in there makes it not unique because you can choose any value of C you want. So find the particular solution of, in this case, we get an initial value problem, 3x y prime minus y is equal to ln of x plus 1. And in this case, again, we are going to keep x positive. Sorry for this zooming in. I don't know why it's doing that. And then y of 1 is equal to 2. So I give you a particular point on this curve. Actually, it's going to be y of 1 is equal to minus 2. Sorry, I wrote that down wrong. Okay, so we have a procedure for this, right? If we look back at what we did with the last example, we started by putting it into standard form. then we found the integrating factor. Then once we had the integrating factor, we solved for y. And it's a fairly straightforward process now, right? It's just a lot of integrals, but that's about it. So let's put it in standard form first. So standard form is going to give me, so you can rearrange this yourself. I'm going to do it all in one step. Y prime and then minus 1 over 3x y is equal to ln of x plus 1 divided by 3x. And of course, we can divide by that x because we're assuming that x is positive. And in this case, p of x is equal to minus 1 over 3x. And q of x is equal to ln of x plus 1 divided by 3x. Okay, now let's find the integrating factor. So my integrating factor in this case, v is equal to e to the antiderivative of p of x dx, which in my case is given by minus 1 over 3 x to the minus 1/3 dx. Or sorry, x to the minus 1, pardon me. Which is equal to e to the minus 1/3 ln of x, which we can do exactly the same trick as before. This becomes e to the ln of x to the minus 1/3, and the e and the ln cancel each other out, and I get x to the minus 1/3 here, which is my integrating factor. Now that I have my integrating factor, I can multiply my differential equation by this. And so this is going to give me, so multiply by v. So I get x to the minus 1/3 and then y prime minus 1 over 3x y. And then this is equal to my q, or my v, like this, and then multiplied by q, ln of x plus 1 divided by 3x. So we've got a lot of simplifying that we can do here. The first thing is, we already know with this integrating factor, this is going to become the derivative of x to the minus 1/3 y. So after you compactify, if that's a word, up the product rule here. And then you get 1/3, I'll leave that out front, and then ln of x plus 1 multiplied by x to the minus 1/3 here. Sorry, x to the minus 4/3, because we had an x in the denominator already. Okay, so that means that if I integrate, I get x to the minus 1/3 y is equal to 1/3, 1/3 times the integral of ln of x plus 1 x to the minus 4 over 3 dx. Now, we've been doing this a lot, right? We are self-described experts at doing integration. So let's put that to the test. What I look at when I see this integration problem is I see an ln of x multiplied by not a polynomial, but x to some power. And we should remember from all of the practice that we've had that when we see this type of integral, we should be thinking integration by parts to solve this thing. So let's go ahead and use integration by parts here. So let me do this integral off to the side. So I get 1 over 3 ln of x plus 1, and then x to the minus 4/3 dx. In this case, maybe I'll put this down here. So u is equal to, and v prime is equal to. Now, maybe these aren't great notations because v has already been used for the integrating factor. I hope that you can realize that this is just my little scribbles for integration by parts, right? And so I want my ln of x to differentiate away. And so I'm going to have this right here. And so that tells me that u prime is equal to 1 over x, because that's the piece I want to differentiate away. And actually, I can put that 1/3 from out front there. And then this is going to give me minus x to the minus 1/3 for this antiderivative. And so this whole integral from integration by parts becomes minus x to the minus 1/3, and then times u, so ln of x plus 1. And then plus, the reason I have a plus here is because this term right down here, v, has a negative in it. So multiplying the minus from integration by parts with that minus gives me a plus. And then I get u prime times v. So that is 1 over x times x to the minus 1/3. That is x to the minus 4/3 dx, which now we've already actually done this integration. So let's write it all out. We get, in this case, you get minus 3x to the minus 1/3 plus c. Okay, so that was, that was a tedious application of integration by parts, but we are experts at integration at this point, right? So we can do that. And so therefore, x to the minus 1/3 y is equal to minus x to the minus 1/3 ln of x plus 1 minus 3x to the minus 1/3, and then plus c. And so therefore y is equal to ln of x. I'm going to get a plus 1 from this piece, and I'm going to get a minus 3 from this piece. I'm actually going to get a minus 1 here. So this becomes minus ln of x minus 4 plus c x to the 1/3 after multiplying through by x to the 1/3 to get rid of the x to the minus 1/3 on the left-hand side. So this is my solution to my differential equation right here. What I have written in this final row, this is the family of solutions. We call it the general solution. It's general because you can still pick the value of c. But now, find c using the fact that y of 1 is equal to minus 2. Well, this is going to give me minus 2, so that's the y value on the left-hand side, is equal to minus ln of 1 minus 4 plus c times 1 to the 1/3. And so I get minus 2, ln of 1 is 0, minus 4 plus c, which gives me that c is equal to 2. And therefore, my particular solution, y, is equal to minus ln of x minus 4 plus 2x to the 1/3. So it's a little bit of an ugly function, but it's a function nonetheless, right? And so now we have a general method or general algorithm, if you will, to solve these linear first order differential equations. So what I want you to keep in mind is that the derivation of the solution was a lot harder than applying the solution. When you are faced with these problems in exercises and on tests and on assignments and etc., a lot of what you're going to do is just follow the procedure, right? So put it in standard form, find the integrating factor, multiply through by the integrating factor, and then do the appropriate integrals, right? So it's a fairly easy procedure now that we know what we're looking for. And most of it, like most of the stuff that we've been learning, boils down to just finding an antiderivative using an integral.